in the remaining part of this lecture series as an application of our theory of root space decomposition of the Lie algebra SLNC over C. We will talk about the simplicity of this Lie algebra SLNC for n greater or equal to 2. What do we mean by simplicity? What do we mean by simplicity? Let A containing this G, which is our notation for SLNC, be a non-zero ideal. We want to show that A is a whole space G. So the simplicity here simply means any ideal in a Lie algebra is either 0 or the whole space. The proof is as follows. We consider the following two cases. Case 1. If this ideal A is containing H, remember the H denote the Lie subalgebra of all the diagonal matrices in G. And this H, remember, is properly contained in G. This H is not the whole G, because those E sub ij's for I not equal to j is not in H, but they are in G, because the diagonal entries are all equal to 0. In particular, the trace is equal to 0. Under this situation, since we assume that A is non-zero at the beginning, now, by this assumption, A is also properly contained in G. We expect a contradiction. So the goal is the following. We want to get a contradiction to that the ideal A is not equal to 0. Now let's see how to find this contradiction. Let H be a non-zero element in A, which is contained in this bracket H. Since, remember H star, which is a space of linear functionals on H, complex linear functionals. This is spanned by E sub I minus E sub j's. For all pairs ij with I not equal to j. Remember, by our notation, this set is called delta, the set of roots. Because of this, there exists some E sub I minus E sub j, a root such that E sub I minus E sub j applied to H is non-zero. Do you see why this is true? This is because if E sub I minus E sub j applied to H, which by definition is the i's component on its diagonal line minus its j's components on its diagonal line, is equal to 0 for any I not equal to j. then H must be a scalar matrix. From here, all the entries must be equal on its diagonal line. And H is already a diagonal matrix by definition. Since H belongs to this least set of algebra H consisting of all diagonal matrices. But H as a matrix in G, which is SL in C, the summation of its diagonal matrix must be equal to 0. Namely, n times H1 must be equal to 0. This, together with the fact that the characteristic of the complex numbers of C is equal to 0, implies that H1 is equal to 0. And this is a contradiction to the assumption that H is non-zero. And this contradiction proves that the existence of such AI minus AJs with E sub I minus E sub j of H not equal to 0. Now, using this particular EI minus EJ, we consider the least set of algebra E sub EI minus EJ. This is a one-dimensional least set of algebra spanned by E sub ij's. And remember, E sub I minus E sub j of H applied to E sub ij is equal to, we did this computation before when we were discussing the root space decomposition for SL and C. The Lie bracket of H and E sub ij. But because this H is taken from A, so this Lie bracket must give an element that is contained in A, because A is an ideal, which in particular is contained in H, because we assumed that A is contained in H. Now we see a contradiction, because this part as a scalar is non-zero by our choice above. Now, if we divide both sides by this non-zero number, we'll get E sub ij is in the 1 over E sub I minus E sub j applied to H dot H, which is simply H. H is a complex Lie algebra, so the scalar will be absorbed into H. And this will be a contradiction to the definition of H. The origin of this contradiction comes from the fact that H here is non-zero. Namely, if we assume that this ideal A is non-zero, then there exists a non-zero H, which implies that E sub I minus E sub j applied to H is not equal to 0 for some I not equal to j, which will lead all the way to
E sub ij belongs to H for this particular ij. And that is a contradiction. This finishes our first case.